Alright, so one quick note before I get into the topic for today. I want to remind you that on lecture videos, a good way to get through lecture videos is to play them at a faster speed. So I usually watch lecture videos at anywhere from 1.2 to 1.5 playback speed, and then I pause when I need to. And I do that instead of playing it back at normal speed without pausing. That usually gets you through it a little bit quicker. And typically somebody's speaking at a slower pace than you can actually understand them. So you can usually retain it the same amount if you watch it at a little bit quicker pace. Alright, so in this next two set of lecture slides, we're going to be talking about an extremely fun problem called the selection problem. We're going to look at it once using a stochastic algorithm, and again, we'll look at it using a deterministic algorithm. So what is the selection problem? Well, as input, you have a set of n numbers. It doesn't have to be n numbers. You could do this with words as well, but it's easier to discuss if we're talking about it in terms of numbers. And your second input is a value I, where I is inclusive 1 to n. And your output is going to be the element that is larger than exactly I minus 1 other elements. This is known as the ith order statistic, and you can think of this as just the ith smallest number. So when I is equal to 1, and you plug that in up here, 1 minus 1 is 0, so there are no elements. This element is larger than no other elements, so that would be the smallest number. The minimum element is the first order statistic. The maximum element is the element that's greater than n minus 1 elements. So you've got the nth element, it's greater than all the other n minus 1 elements, and that's the maximum element. It's the nth order statistic. Alright, well, what is I for the median then? So this will be an expression based on n. You just have to tell me a value for the order statistic for the median value. Well, this will depend on if you have an odd or an even number, but if n is even, then the medians, there are going to be two median values. So if you think about having four numbers, 3, 16, -5, and 12. If I have those two numbers, the two median numbers are going to be 12 and 3. So if I sort this, it would be the n over 2 and n over 2 plus 1 order statistics. Indices, but it would be the n over 2 and n over 2 plus 1 order statistics. If n is odd, then it's n plus 1 over 2. It's the n plus 1 over 2 order statistic. Okay, well, let's first solve this problem using a method known as reduction. So if I want to find the ith smallest number in an array, I kind of got ahead of myself when I was talking about if I had sorted things and talking about n over 2 and n over 2 plus 1. Well, that's one way we could solve this problem. If we sort our input and then just return the item at index I minus 1, we'll get the ith order statistic. So if I sort it and I want to get the smallest number, that's the first order statistic. That would be getting the element at index 0, which would be the smallest number. So that's one way to solve this problem. That's big O of n log n. We're going to look at two algorithms for solving this in faster than n log n time. Okay, so how do we do better than n log n? Well, we cannot sort because for any comparison-based sorting, that has to take at least big O of n log n amount of time. That's something we'll prove pretty shortly here, and the next topic after the selection problem will be proving that lower bound. Do we even need to perform a comparison with all elements? So basically, what's the fastest we could possibly do this? Well, yeah, we have to at least look at every single element. So that means, so for example, if we have n elements, you can't get away with just looking at half of them if I want to find the smallest element, or if I want to find the middle element. I have to look at all n elements. So we know that big O of n is a lower bound on our running time. What's a reasonable upper bound on our running time? Well, this is sort of a trick question because you can take as long as you want, right? I could write an n factorial, big O n factorial algorithm for solving this that just wastes a lot of time. But I think it's pretty reasonable to assume that if you compared every element to every other element and had an n squared algorithm, that's sort of a reasonable upper bound. You shouldn't expect to ever do worse than that. All right, in the next set of slides, we'll look at a couple of edge cases and then build on from there.